So, we have looked at the idea of tangent lines extensively, right? We have done a lot of stuff with derivatives, which is slope of the tangent line. So we've looked at those extensively. We have also began work on the area under the curve, right? We've looked at Riemann sums and different things. So mathematicians were already working on that stuff before calculus was developed. So some of the mathematicians who worked on derivatives are listed here. Some of the ones who were working on integrals are listed here. So you can see Isaac Barrow was in both lists right there. So he very well could have been one of them that could have came up with calculus, but he didn't. He was beaten by the other. So there was already people thinking about those ideas. What no one understood was that they were inverses of each other, right? That the tangent line of a curve was the inverse of the area under the curve. They did not understand that. So they were working on derivatives. They were probably coming up with rules for derivatives. I have not studied this extensively to know who exactly was doing what pre-calculus, right? But they were coming up with this. They probably had rules for taking derivatives, like power rule and stuff here. They probably knew how to go backwards, like how to find, I knew that this was my function, so if I wanted to go backwards from the derivative back to the function, they probably knew how to do that, like you guys were, whenever you guys had that worksheet before you did the notes, did you guys do that yesterday? Could you guys figure that out on your own pretty well? Like, you guys were able to come up with that on your own. So they were coming up with stuff like this. They could go backwards. What no one understood was that when they were going backwards, when they were going from the derivative back to the function, that was the same as finding the area under the curve. So it was huge that those two were actually inverses of each other, because it took these two ideas that didn't necessarily seem to be related to each other and put them together and made them so applicable in so many different types of contexts. So it's not so much that Isaac Newton and or Gottfried Leibniz came up with every part of calculus on their own. They were taking stuff that had already been worked on, and they were putting that together and recognizing that it was inverses. There is a bitter feud over who actually discovered calculus. I read a whole book on it last year called The Calculus Wars. It was great. One of the trainings I went to for AP Calculus suggested it, and I would highly recommend if you are a calculus nerd, because it's really interesting. So what happened is Isaac Newton began his work on calculus early. So he began working on calculus before Leibniz did. So he was doing all this, but Newton had published some work on other stuff and received harsh criticism of his work, to the point where he did not want to publish anything anymore. So he's like, fine, I'm just going to do all this work, and they can publish it when I'm dead. I'm not publishing anything anymore because I don't want people telling me I'm wrong on things. So that was his mindset for a while anyway. And he did all this work on calculus and had discovered, the inverses and derivatives or that integrals and derivatives were inverses of each other, and was developing rules for things on how to do these different calculations. And he had came up with all that. Meanwhile, in Germany, Gottfried Leibniz began his work on calculus and figured out basically the same stuff Isaac Newton had figured out. And Leibniz published first. So he published his work before Newton, although it is said that Newton began his work before Leibniz. So then Newton accused Leibniz of stealing his work. And once Leibniz had published his work, Newton published his work and was like, hey, he stole this from me. And Leibniz said, no, I didn't steal it. This is my own work. You stole your work from me. And they hated each other. And at the time, there was like a royal council of something or another. You can tell I'm not remembering details from this book very well, but I think it was called like the Royal Society, maybe. Anyway, it was like a meeting of the minds sort of thing. Like all these people right here, the ones that were still alive anyway. Another one the book talks about a lot, they weren't mathematicians, but Bernoulli, which is, I remember that from science. They were brothers, I think. And there was, what did Bernoulli do in science? I can't remember, but I remember it from science. But, a lot of these people were all, like, alive and were in, like, the society where they would go and, like, talk about different discoveries and stuff that they had made. So, there was an investigation into who actually was the founder of calculus, and that investigation concluded that it was, in fact, Isaac Newton. However, this investigation was conducted by this Royal Society. Guess who was the president of the Royal Society at the time that they concluded that Isaac Newton created calculus? Isaac Newton. So, take that for what you will on that conclusion of the validity of the investigation. I'm not sure. Yeah. So, anyway, it's really interesting. I would like to know more. That book was really good if you're interested in that sort of stuff. It was written pretty well for something that like is not super like, huh? They would get like fellowships. I think I'm not exactly sure. I know that Leibniz had this like big project of making these like windmills and something. Anyway, it failed miserably. He was working on it a lot of times while he was working on calculus. He was paid for that. I think maybe Leibniz like had some sort of job at a library that something or another. I don't know. Yeah, but they were like paid to do these things through different ways. I don't know exactly. I mean, I'm not exactly sure exactly how it was funded, but it's really interesting. What was really interesting in that book to me was like the number of like names of mathematicians and scientists that I had heard of before that were all like alive at the same time and making these big discoveries, kind of like all at the same time. Yeah, they should. They should spice it up a little bit with like all the rumors and yeah. So yeah, until gravity is created. Yeah, you're right. But it's very interesting. I will say like Leibniz, we use more of his notation. Newton's notation was much messier. I would love to see like a copy of their actual work as it was published, because I'm pretty sure I would have a hard time understanding any of it, even though I understand calculus, because at least Newton, the book showed a little bit of Newton's notation, and it was not anything we're familiar with because we don't use it. We use Leibniz's notation more. The book that I read generally seemed to hold the opinion that both of these men probably independently, without stealing work from each other, came up with calculus, because there had been so much work done on it already that it was sort of inevitable that somebody was going to figure this out at some point. Like I said, Isaac Barrow here, he could have been in the running. He'd done work on both. He just had not recognized the relationship between the two. So anyway, this is a big deal. It is what pulls calculus together, because otherwise calculus is just like a study of two separate things. So it's a really big deal. So the fundamental theorem of calculus connects integration and differentiation. So far we have talked about derivatives. They are slope of a tangent line, integrals, or area under the curve. The fundamental theorem of calculus tells us that if f is a continuous continuous function on an interval containing a and b. Okay, now y'all ready for this? This is a big deal. Okay, the derivative of the inverse of a function just equals that function. So if we take the derivative of an inverse of a function, it just gives us that function because the derivative and the inverse are inverse. I'm saying inverse. The derivative of the integral of a function is that function because derivatives and integrals are inverses of each other. So this was the big discovery that exactly. Like, it's like if you add x plus 1 and x minus 1 undo each other. That was the discovery. Except for with derivatives and integrals there. That made such a big deal. Yeah. So, it is a huge deal in mathematics because it puts these two branches together as one like cohesive unit that can be used for lots of different things. But the problems we're going to do today should not be terribly difficult for you. So, let's look at what this is going to look like. Okay, so, now something that you need to note, we're doing the derivative of the integral from 2 to x of t squared minus 4t dt. A couple things to note right here. This number right here must be a constant. It can be any number in the world, but it has to be a number. If it is a variable, then you're going to have to do something different. We'll learn how to deal with that later. But it's going to have to be a number right there. So we're going from 2 to x, so this can be a variable. But what cannot happen is these variables right here cannot match. Okay? So right here, this variable and whatever variable you're integrating with respect to cannot be the same variable. Right. And what we're usually going to see most of the time for these problems is that the x is here on our integral. So that our answer is going to be in terms of x. And whatever's inside of the function is what I like to call like a dummy variable. It's there in place of where we're going to put the x. So we'll see t's, we'll see k's, we'll see different variables there. We could technically have a different variable here as well, but most of the time we're going to see an x there. So the derivative and the integral undo each other here. So it would just give us the function, but we are going to plug in the x instead of the t for that. So the answer for this would be x squared minus 4x. Yeah, fundamental theorem of calculus is huge as far as mathematical discoveries. Not terribly difficult as far as actually evaluating the problems that we're going to be given. Yeah, the answer is basically the function, right? The only thing that we got to do, so like for this next one, the only thing we got to do is where I've got the x right here, this dk right here, I'm replacing this k because that's the variable that I'm taking the derivative with respect to. I'm replacing it with whatever variable I have here. So my answer here would be e to the x plus 4. There's going to be one more little twist. It's not huge, though.
Why not just have it be x? Like you're going to replace it.
When we do definite intervals, I can answer that question a little bit better. So when we look at the other way to deal with this kind of, I can answer it because here, what's happening is you're replacing the variable here with your limits. You would also replace it with 1 when we're doing definite intervals, which we'll see. So if x is here, it becomes part. If x is in both places, then it has to be integrated over here. Whereas if it's see here, we're integrating with respect to k. It's not super easy to explain right at the moment. So I'm going to have to kind of leave it till we do definite integrals soon, and it'll hopefully I can give a better explanation. Okay, now, yes? Right. What we're doing is we're not actually, we're so we don't know how to do definite integrals yet. Is the reason I can't answer your question very well either. But whenever these are definite integrals, so they are from a point to another point. So what you guys were working on yesterday, where you put the plus c on the end, was indefinite integration because you just had the integral symbol. It was not looking for the area under the curve from 2 to 7. It was generally looking at the function. So there's a little bit of a difference there. When we get to definite integration, I'll show you why we don't need the plus c here. But for right now, we're not actually integrating like we could, although we don't know how to do definite integrals yet, because we don't know how to do those there. We could integrate it and then take the derivative. But because they're inverses of each other, there's no need to do that. So we're skipping that. In fact, I'm not even teaching you that step yet, how to integrate and then take the derivative. I'm just showing you these are inverses. So if we see a problem where we're taking the derivative of an integral, we don't even need to try. Does that make sense? Okay. So now there is going to be a little bit of a difference here. Whenever we have a problem that looks like this one here. So if you're going from a constant to an x, then you don't have to do anything special. It is just going to be the function with the x plugged in. If we have here this number right here, this a right here, that is still a constant. But this time, right here, instead of just having x, we have g of x. Which means that we could have something like x squared, or x plus 2, or 5x minus 7, or e to the x. We've got some expression that's more than just an x. Or technically, I guess it could just be the x. It will still work. So, if we are doing this, we are still going to take whatever is here, we're going to plug it in for that dummy variable, right? So we're plugging it in for in this case, t, because it's in terms of t. And so our answer will be f of g of x, but we must multiply it by the derivative of g. It's like a chain rule here because we're taking the derivative and the integral rules, like the derivative rules out the integral here and gives you the function. But because you're taking of the derivative of something that's basically like a chain rule here, you have to multiply by that derivative of whatever g is. Okay? So let's see what this will look like here. We have got a constant as our term. We are going to have to take x squared and plug it in for the variable that we are integrating with respect to, which is our a. So that x squared is going to go everywhere that we have an a. So we'll have x squared minus x squared squared over 4x squared. And we must multiply that by the derivative of x squared, which would be 2x. Technically, you can use the same rule if you just have an x, because what's the derivative of x? 1, so it basically just, you can use the same rule. So if we simplify this a little bit, we've got x squared minus x to the 4th over 4x squared times 2x over 1. I would probably do this. I would probably factor out a x squared. We got 1 minus x squared here. 4x squared times 2x over 1, like that. And this x squared can cancel with this x squared in the bottom. And I would reduce this and make it a 1 and this a 2. So we would have x times 1 minus x squared over 2. I put this x out front right here. Okay, does that make sense what we're doing there? All right, so if we have something like the derivative of the integral of 8t squared minus 4 dt, and we're using the square root of x, we would be plugging in the square root of x there for our t. So we would get 8 square root of x squared minus 4 times the derivative of the square root of x, which is 1/2 x to the negative 1/2. So this ends up being 8x minus 4, and this is 1 over 2 root x. So I would make that 8x minus 4 over 2 root x, and they would probably reduce that and make it 4x minus 2 over the square root of x for that. See on this how I did that. This next one just to see if I did the shortcut or if I just multiplied it out. Okay, oh, I see what we did. We just didn't even, we didn't simple, okay, got it. That'll be better. All right. So, actually, so I was thinking to myself this was going to take forever to multiply out, but you don't necessarily have to multiply it out. So, if we're taking the derivative of the integral, we're going to plug in right here for our t, which is our variable of integration. And so we will get x squared minus 3x plus 1 cubed. And then we must multiply it by the derivative of the thing that we plugged in. What is that? 2x minus 3. And I'm glad that I looked at what I did last year, because in my mind I was thinking we needed to multiply that all out. Most of the time it will not be multiplied out in the answer key. It'll just be left like this. So, yeah. And even on multiple choice, they probably are going to leave the answer choices looking like this instead of multiplying it out, because it's going to take a while to multiply that out. Okay, questions? Okay. All right, let's look at a couple more things. Okay. Let f be the function given by the integral from -2 to x of g of t dt, where g is a differentiable function. The table above gives selected values of f, g, and g prime, and h is the function given by h of x equals 2x plus sine of x. For what value of x is h of x equal to f prime of 2? Okay, so this has got a lot of parts to it. It's calculator active. So the first thing we need to worry about is this f prime of 2. Okay? So f of x equals the integral from -2 to x of g of t dt. So if I want to take f prime of x, that means I'm taking the derivative of the integral from -2 of x g of t dt. What is the derivative of the integral from -2 to x of g of t dt? It is g. It's g of x, because that x will get plugged in for that dummy variable there. So basically, f prime of x is just equal to g of x. Right? So f prime of 2 will equal g of 2. And from our table, what is g of 2? G of 2 is -2. We're looking right here. So that is our f prime of 2. Right? Then we want to know where h equals f prime of 2. So h is 2x plus sine x, and we want to know where that equals -2. So, on our calculators, oh wait, that's the wrong thing. I would probably actually use the graph on this, and the reason I say to use the graph, it might work with the solve feature, but a lot of times with the solve feature, when you got trig, it just doesn't work out. So I would, if we want to use the graph, we can just put 2x plus sine x in y1, and I'm going to put -2 in y2. And I just want to see where those cross. So if I go to my graph, I can see that they're going to cross over here. And actually, just looking at my answer choices, which one's going to be right? Should be the first one, because it's the only negative value I've got. But let's find that value exactly. So if I do F5, and I want to know the intersection, which is number 5. When you do intersection, it's going to say first curve, and as long as you've only got two equations in, it should work fine. Just hit enter, and second curve, enter, and then my picture is really bad, but the lower bound, you can just type in numbers. I'm going to put like -2. Oh, it's outside the window, sorry. Let me try that again. I'm going to type in -1. And I know like 0 would be above it. And that's going to give me this point right here, which is -0.6, -0.684, which is A. What did you get? Did you use the intersection?
You just like, do you have to go anywhere for the picture? Or do you just click enter?
As long as you only got 2, you can just click enter. And then I put in -1 for my lower bound and 0 for my upper bound.
Oh, you typed it in?
You can. You don't have to. But sometimes I get very impatient with the little spider moving.
Oh, I didn't move it.
Yeah.
Wait, so what do you do?
Lower bound is really like a left bound. You need to be on the x-axis. You need to be below of the place where they cross. So since they cross, yeah, since they cross like right here, I did -1 because that's about as far as I can go to the left of that, and then I did 0. Okay, let's look at a couple more of these. Your assignment tonight is going to be from Delta Math, which I probably need. No, yeah, I need to change the date on because we were supposed to do it Tuesday. But yeah, but it is Delta Math problems are basically going to be these problems, right? So that's basically what you're going to be doing. But I wanted you to see some of these. So I've got these. 2 more that hopefully we're going to get done, and then you'll have the last 3 to do also in addition to your Delta Math that you'll do on your own. So, so let's look at this one. The figure above shows the graph of the differentiable function g and the line tangent to the graph of g at the point 3, 4. F is the integral from 0 to x of g of t dt. H is the function given here. If the line tangent to the graph of h at x equals a is parallel to the line tangent to the graph of f at x equals 3, what is the value of a? Okay, now reading and figuring out all the pieces here is the hardest part. So, line tangent to the graph of h, what's that? At x equals a. What is the line tangent to the graph of h? What? H prime. Okay? It is parallel to the line tangent to the graph of f. So h prime of a, which is my slope of my tangent line of h, has to equal f prime of a. But what is f prime of a? If I take the f is right here. F is what we call an integral defined function. So if I take the derivative of this integral right here, what am I going to get? Just g of x. Right? So h prime of a is going to equal g of a. All right. And in particular, they're telling us at 3. I shouldn't say a. I guess I should say 3 for this one because it said at 3. Let's change that to a 3. What is g of 3? G of 3 is 4. It is just the value. Because they're not asking us for the slope of the tangent line of the graph we're looking at. They're asking us for the slope of the tangent line of f, which is just g. So that equals 4. So then this one, I don't know if it's going to solve it or not. You could use the table. It might solve it. Doesn't work with Solvematics. Good, I'm glad you're a step ahead. Yeah, in general, I try to stay away from using solve if there is trig because it doesn't like it most of the time. So x times e to the, cosine x. And then I'm plugging in 4 right here. And I'm going to go to my window and make this from 0 to 7 because it tells us that's the interval we're looking on. And I'm going to graph it and see what happens. 4. So you're it's telling you at x equals 3, so you're looking for f prime of 3, which is g of 3. And so if you look at your graph, g of 3 is 4. So in that y2, I'm putting 4. And for this graph, our multiple choice here, 1, 2, 3, 4. It's between 4 and 5. It looks more like D to me. Has somebody found that intersection so we can move on because we're running out of time? It's closest to D. Yeah. Yeah, since it's multiple choice. To be sure, I like to actually find the point, but we're running out of time. Okay. And we're out of time. We'll just look at this tomorrow. Not tomorrow. I've only been here one day this week before today, so it feels so. Yeah, number 2 you can skip, but do try number 1 and number 3 there. And then you have a Delta Math assignment that I need to change the date on because it's going to look like it's in the late credit. So let me change this date to Monday at 8:30. All right. I think it is correct. So do the Delta Math. Look at those couple other questions too, and we'll look at that last one maybe as our warm-up or something on Monday. Oh, did you guys did everybody pick up somebody did not pick up their FRQ assignments for next week. That would be me. Oh. Okay. Look at all this. There's like nothing in my book now. All right.
So during third, I can come in.
Yes, during third will be fine.
Also, you have a recommendation for arm shield.
Yes. Yeah, just send me the link. Those are due mid-February, right? 17th. Okay. Yeah. I will be glad to. Have a good weekend, everybody. Good morning. I do not know why you have a Diet Mountain Dew on your desk, but I think Connor Ball is probably responsible for that. Is it empty or is it? It was empty, we just said. Are you ready to fail? Let's go!
Alright, Liam's. I really sleep this morning. I was so excited for this. I just stand there and act like I'm doing something.
Are you ready for the movie?
No, I think we're all carpooling.
This is maybe your charger.
I don't know. I think we might just all load up in.
Are you missing one? Possibly.
Load up in his.
What's that?
Yes. Thank you.
You're welcome.
I don't even know what it is.
Sorry. Smith, I went to unplug mine, right?
Okay, let's.
Last week or whatever. Yours is there. And your carpool is gone. I'm like, I'm not gonna take it.